All right, we're going to talk about something really exciting to me. I think that regression and logistic regression are really underutilized tools for most of the people who do applied research. And there's probably some pretty good reasons. It takes a little bit of extra training, but conceptually it's a little bit harder to explain to other practitioners. So let's go really quickly over ANOVA. ANOVA is an analysis of variance, and there are a variety of these versions of ANOVA, the MANOVA, and anyway. But really, what we're doing is we're doing a t-test for multiple groups, and they're simultaneously testing if there's any difference in any of those groups. So, if we looked at contingency tables, we were looking at percentages in different columns to try and see if what we saw was different than what we expected. Well, think about a t-test. The t-test compares the differences of means as well as their variation, the standard error, to see how closely they're related, or the probability that they're drawn from the same groups. ANOVA does this where we test between groups and within groups. So it's a pretty powerful tool. A guy named R.A. Fisher created ANOVA, and it's F for Fisher. So if you saw like a chi-square and then a number, chi-square equals blah, 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 P equals probability that the null hypothesis is true. A t-test does the same thing. T is a measure of difference, and you use that with a probability associated with the probability of the null hypothesis being true. The F test is the same thing. You calculate some test, F equals something, comma, P equals whatever. So whenever you see a test, you can know what kind of test it was. Chi-square test, t-test, F, some version of ANOVA. So how do you know if ANOVA is the right thing? Are you looking for variables or explaining the difference between groups on one or more variables? Okay, yes. Well, are they the same participants being tested? No. So it's not a repeated measure. How many groups are you dealing with? One group or more than two groups or more than one group? Or more than two groups. If there's more than two groups, this is a simple ANOVA, as long as we're not doing the same people over and over and over again. So you can use this sort of like flow chart to try to identify which test you're supposed to be using. There's all sorts of different versions of ANOVA. And we can do one-way simple ANOVAs, we can do single-factor ANOVAs, that's a single grouping factor, or there's two-way ANOVAs, these are more complicated, but really they all do the same thing. What we're doing is we're testing the means and the variances between different groups, but also within different sets of treatments. And we'll give you a two-way ANOVA factorial design. This is an example where we're looking at males and females when it comes to success in student achievement, when it comes to number of hours per preschool per week. So if we look, there's a grouping variable here, which is gender. But the number of hours in preschool, these are different types of treatments. So we're looking at 3 different types of treatments over 2 groups. That's actually 6 different groups. A t-test really only compares 2 different groups. And so a contingency table or a chi-square test will compare expected results in different cells, and you can have a gigantic contingency table and chi-square test. But if we want to compare means, ANOVA is the way to do that. So in each of these different cells, we have males 5 hours, males 10 hours, males 20 hours. These groups of males get treated 3 different types of treatments. Females, same thing, 3 different types of treatments. So we're looking at the effect of the treatment as well as whether or not there's differences in groups. So that's more or less what ANOVA does. When you calculate it in something like SPSS or Stata or R, you get a source table. The source table just more or less tells you whether or not, what the differences are between the groups and within the groups. So between the groups would be between males and females. Within the groups would be the different types of treatments. And then the only thing that really, really matters is this F number, F 8.799. And that has an associated probability. So you can generate the degrees of freedom. Really, we don't even do that anymore. The computer program does that for us. We could look that up in a table, blah, blah, blah. It doesn't really matter. What we end up with is something like this. And this, if you were writing out a paper and we said, hey, we conducted an ANOVA test and found that there was a statistically significant difference. You put up a parenthesis, you write F equals 8.80, comma, P less than 0.05. And this is shorthand for look, we obtained a difference value of 8.8, and it has an associated probability that the null hypothesis is true. That probability is 5%, less than 5% chance that the null hypothesis is true. So what does that mean? It means that there's a difference somewhere in those 6 groups, somewhere between the groups or within the groups. One of those cells, at least, is different than the others. And that's what an omnibus test is. An omnibus test means that somewhere in that group, among those groups, 2 different groups, could be all 6, that they're different. So in order to figure out which one is different, you have to conduct follow-up t-tests. And every time you do that, you increase the likelihood of making a type 1 error. So it's possible that you don't find a difference, or you do find a difference when it's not there. Now, there's so many different possible ways to do this, but I want to point out an easy way to do it. When you do an ANOVA, it'll give you this output, and this is only just one of those groups, is males or females. I don't exactly remember which one. In these different treatments, it'll give you a mean for the treatment type. So for 5 hours, that's 76. For 10 hours, it was 85. For 20 hours, it was 91. Where we go first is we look at the ANOVA. Down here, between groups, within groups, doesn't really matter. Look for the F, 8.799, and the SIG, 0.001. What? Yeah, there's like a 99% chance that there's a difference between groups, or there's less than a 0.1 chance that there's no difference. Remember that the SIG and the P are the same. They both test the probability that the null hypothesis is true. So we go over here and we look at these scores. Well, how do we know which one is different? We could go back and do follow-up t-tests, but the problem is we might be not able to adequately assess the differences. So what we can do is we can go over here to this 95% confidence interval for the mean. And the 95% confidence interval is to say, for this 5-hour group treatment, we're 95% confident that the true mean is between 68 and 85. So whatever the mean actually is, we're 95% confident it's in between those 2 numbers. Now, if these bounds overlap, if these confidence intervals overlap with any other group, then you won't know if that is a real difference. So for example, these 2 overlap between 10 hours and 20 hours. 80.77 and 89, up to 89.63 and 89.16 to 94.01. 04. Those 2 numbers overlap. So there is a probability that those 2 groups are actually the same. Well, how could that happen? Well, because their ranges overlap. But if you compare the 5-hour treatment to the 20-hour treatment, the 5-hour treatment is here between 68 and 85, and the 20-hour treatment is between 89 and 94, those 2 groups are statistically significantly different at the 95 confidence interval. So the output from SPSS or R or Stata or any of these other stats programs will give you the tools to see which groups are different. That's probably the best way to do follow-up to see which groups are different. Okay, so I want to talk about regression. ANOVA is the first step in calculating regression, but regression is a method of hypothesis testing that is a more complete combination of correlation and ANOVA. When we did a scatter plot before, we plotted the XY coordinates and we clicked draw a line here in Excel, or maybe we did one in SPSS. It was drawing a line of where it would best fit those points on that scatter plot to fit the data. Well, that's good, and it'll give you an R value or an R squared value, but it won't tell you whether or not that relationship is a good relationship or not. So we have to estimate a linear relationship between these variables, and what we're going to do is we're going to draw a line that best fits, that best minimizes the sum of squared differences. That is to say, the difference between what we predict and what we actually see. So imagine drawing a scatter plot and then drawing the difference between those the data points and the line of best fit, and then taking those errors in your prediction and running them through an ANOVA. And so it's kind of a more complex way to think about things, but maybe when you were in elementary school, middle school, high school, they gave you this formula, y equals mx plus b. Well, in statistics, we have the same formula, y equals mx, which is bx plus mx plus b at a. A happens to be the intercept, just like b was in your initial line. Then the big beta x is the slope times that variable. So m is still the slope, beta is still the slope. It's slightly twisted around a little bit. Y becomes a constant. That's the y-intercept when x equals 0. But we have this little thing over here, e. What's e? It's error. So we recognize that in our prediction of a linear regression, that those data points don't actually fit all the time. And so E is a representation of the error between the data points and the line that we draw on the scatter plot. So if we're drawing this, regression model, X is on the bottom, Y is on the vertical axis, we would find A where X equals 0. We would also see that in that scatter plot, there's a difference between the data points and that line, the predicted line. So that's represented by E. The B is the slope of that line. Okay, well, how do we get the B? Well, we end up trying to estimate all of these different things. B hat is a prediction of that line's slope. And how do we get that slope line? Well, these are the sum of these, the differences between summing up xy and summing up x and summing up y. And the same thing happens under here. It doesn't really matter how the calculation works, but we're essentially trying to identify where on the x-axis and where on the y-axis each point is. And then trying to estimate a line that minimizes the error or the difference between the data points and the line. So we're trying to draw a line of best fit where we have that error minimized. Then we have to go back in and we plug in this y hat, the prediction line, with the b hat and times the mean. So that gives us how we calculate it. Now in graduate school, I had to do these by hand. I'm not going to make you do those because we have really, really simple tools that can do this for us. So SPSS will do it. Excel will not do it. And you can, Excel will say, well, no, we can run a regression line. No, you really can't. Because the calculations are not always right. So always, if you're going to do a regression, use a verified stats program like Stata or SPSS or R, or even ArcGIS will do some of these things for you. So if I'm reading this output, what does it look like? Well, we ran a model. So the dependent variable, how much do you agree with protecting the environment should be given priority even in an economic recession? This is out of a poll in 2011. This is 10 years old now or more. And we wanted to see whether or not how much do you agree stronger environmental regulations will limit economic growth? So we think that there's a relationship between your perspective about environmental regulations limiting economic growth and whether or not we should protect the environment in an economic recession. So X down here is this predictor of environmental regulations, and Y is protecting the environment should be priority. All right, cool. So we draw this line using the math. And then they look for the ANOVA first quickly. ANOVA is looking to whether or not there's a relationship. So yes, F57 sig is this. The probability of no relationship is essentially 0. If the probability of no relationship is very, very small, that means that the probability of a relationship is very high. Cool. So let's look at that. We have like a 99.9% chance that there's a relationship somewhere. Remember, ANOVA is an omnibus test. It just tells us if there's a relationship somewhere. All right, we go up here to R squared. When we did that, we did an XY scatter plot, we ran a line. The R squared is a PRE statistic. It's a proportional reduction in error statistic. It tells us the amount of error, the amount of the variation in the dependent variable that can be explained by the independent variable. So knowing how much people feel about feel about environmental regulations will limit economic growth predicts about 9% of the variation in how much do you agree protecting the environment should be given priority even in economic recession. So 0.93 is actually very, very small, explaining less than 10% of the variation. Okay, so we're going to go back down here. Down here in this regression, we say constant. So at x equals 0, There's zero support for environmental regulations will limit economic growth. Our prediction is going to be that 2.6, the average score is 2.6, and protecting the environment should be given a priority. What does that mean? Well, we'd have to go back into the data and look what the average range of scores were. But what we find, if we look over here at SIG, we estimate a t, it estimates a t, a difference between the prediction line and the non-prediction line, that is statistically significant. So the constant is significant. We can be pretty sure, 99% positive, that the slope line intercepts the y-axis, the y-axis at 2.6 when x equals 0. Now, what happens here is interesting. If you increase this variable here by 1 unit, how much do you agree stronger environmental regulations limit economic growth? So as we more firmly believe that environmental regulations limit growth, it causes is related to a negative or a reduction in this answer by 0.297. So moving 1 unit on that, how much do you agree stronger environmental regulations limit economic growth, changes the dependent variable by negative 0.297. So they agree less about prioritizing the environment. And we look over here, that's statistically significant. Now, the cool thing about regression, especially just basic ordinary least squares regression, is that a 1 unit change in this independent variable, if it's statistically significant, a 1 unit change is related to a B or beta unit change in the dependent variable. And that's pretty amazing because it allows us for interpreting the individual effects of certain variables on others. And we'll talk about this in just a second, but when you talk about adding multiple variables to a regression, looking at many things that will predict a certain outcome, the stats program will individually estimate that one variable's impact on the dependent variable while controlling for the other variables. So it's a pretty powerful tool. Okay, so why not just do a correlation? Well, bivariate regression has a couple things. First of all, correlation doesn't consider the error or the constant. It just looks at how much things change. And if you look over here, they're really, really similar. So the B value, which is the correlation coefficient, if you just have 2 of those, and this correlation coefficient over here are really, really close. This is negative 0.305 and this is negative 0.297. Wait, how could that happen? If I run a correlation, I get 0.3, and if I run a regression, I get 0.297. Like, what's the difference? Well, it's because a regression calculates the impact of error in your prediction as well as an overall constant. Correlation will just tell you the effect of change. This is why if you collect you click a linear regression line in Excel, you'll get an estimate and it'll be close, but it won't be really precise and it won't tell you if there's a statistically significant relationship. It'll just tell you how much they're related to each other. That's why it's important to run a regression instead of a correlation, because you get an estimate of whether or not it's statistically significant. You get this R-squared value, which is how much prediction you get. You can get that in a correlation as well, but you get actually a more precise estimate of not just the slope or the correlation, but also the constant, where it actually charts on a map, on a graph. So they're similar, but they don't work as well. So correlation is okay, but bivariate regression, regression with 2 variables, a dependent and an independent variable, is much more preferred if you're trying to figure out individual impacts of an independent variable on a dependent variable. Now, my favorite thing to do is to do something like a multiple regression, where you recognize that there are probably a lot of different factors that are influencing some outcome. We can do this in SPSS or Stata or R, GIS, all these other things. This is a very, very powerful way to test complex relationships. If you go way, way back, we were talking about models and how we had different factors that might influence maybe student achievement or something. Well, what we can do is we can gather the data and put them in a data set. And we tell a computer, this is the dependent variable, and these are the individual predictors that I think might have affected it. So, it might be this, it might be that, it might be that. And we're essentially doing like a multiple hypothesis test where we have 2 or more. Every one of those variables is interval ratio. So what we get is a more complex set of relationships, just like we had, y equals mx plus b, or y equals alpha plus, beta x to whatever. This one right here, bx1, is the first variable, and bx2 is the second variable, all the way up to as many as you want. I mean, there's some problems with doing 50 different 50 different variables if you only have like 70 different data points, but we have some problems. And just like in a scatter plot correlation or a bivariate correlation, we're trying to predict a line. Well, if we add another dimension on it, we end up trying to predict something like a plane. How the data fit in a plane instead of just on a scatter plot. So I like this one because it sort of says, look, we don't actually know how all these variables are working together, but let's estimate the, b hat x1, b hat x2, b hat x3. Like, what we're trying to do is figure out what the individual scatter plots would look like, but recognizing that there might be other relationships in there that are affecting one relationship's impact on the dependent variable or another one. So it allows us to tease out the individual impacts of all these different variables on the outcome. Now, this is called, the most common way to do multiple regression is called ordinary least squares. It's mathematically a lot more simple than the other ones, like generalized least squares or maximum likelihood estimation. The principle behind ordinary least squares is that it's simple, and it tries to minimize the sum of squared errors. Sum of squared errors. The errors are the difference between the prediction line and the data points, and the sum of the squared errors. So we square the errors and then we sum them up. It sounds a lot like chi-square, but essentially what we're doing is we're trying to figure out the prediction line and the difference from the prediction line and add them up in such a way that we can draw a prediction line that minimizes the error. Now, ordinary least squares is called the best linear unbiased estimator. It's called BLUE. It's actually really, really very efficient at estimating relationships. And we have these 4 set of assumptions with ordinary least squares. And you can look them up if you'd like. You can Google them. Even when we violate these assumptions, ordinary least squares works pretty well, but it works the best. It's the most blue when the assumptions are met. Now, the first assumption is called homoscedasticity. That's to say that the variance or the variation is the same across all the variables. Now, that doesn't always hold up, but that's all right. And actually, and also it means that there's no predicted pattern in the error. That's probably the easiest way to think about that. The second assumption is independence of cases. That's to say that each object of study is not related to the other objects of study. If we're looking at cities, and we're looking at Houston, and we're looking at Dallas, and we're looking at El Paso, those are independent cities. There's nothing like Dallas, Fort Worth, and then Fort Worth, Dallas. Those two are related to each other. If we have cases that are not independent, we have something called autocorrelation, and that causes variance estimates to go kind of crazy. The third one is called no multicollinearity. That's to say that 2 of the variables or the characteristics of the cases don't trend together. In other words, there's a correlation between those 2 variables. Let's say we're trying to predict, unemployment, and we're looking at people in poverty and a number of people who are on SNAP benefits. Well, those are related. Poverty is like an undergirding for SNAP benefits. SNAP is food stamps, right? So if those 2 variables are included in the exact same model, trying to predict whatever that was, it's like one of them is trending and the other one is trending the exact same way. And when they do that, it's hard to distinguish which one of those 2 variables is related to the change in the dependent variable, because they're both trending the same way. And when they're trending the same way, it causes our estimate of those relationships to not be very precise. So if we have multicollinearity, we end up getting very large predictive values, but no statistically significant relationships. And that becomes a problem, and we can figure out some other things. The last one is harder. It's non-omitted variable bias. So in other words, we are not missing anything in our model. And this is hard because we don't know what we're missing. If we don't know, we don't know. So this one's the one that's violated the most often. It's also called strict exogeneity or non-endogenous error. In other words, we probably don't know that we're omitting things, because if we were omitting variables, we would probably throw them in. And so this is one of the harder ones. Now, the benefit of ordinary least squares is that it's awesome, and the estimates are really close, even when you violate the assumptions. Some of the violations of the assumptions are more egregious than others, but the cool part about it is that most of the time it still works, even when you don't obey all the rules. Another super cool thing about ordinary least squares is that it controls for the effects of the other variables, and it estimates the individual effect for each of these variables. So I'll show you in just a second, but we could have 5 variables trying to predict some outcome, and the regression will tell us this variable and this variable are related and these are not related. Okay, cool, that's great. But the cool thing is it estimates the individual impact of this one variable while controlling for the effects of the other ones. And it individually impacts the impact of this variable on the dependent variable while controlling for all of the other ones. So that's pretty cool. Another thing is that the coefficients, or the parameter estimates, they're also called beta, they can be directly interpreted. So a 1 unit change in that variable is related to a B unit change in the dependent variable. So what's pretty awesome about that is if you have things like counts or a percentage, and it's measured in actual percentages, and the other variables measured in percentages, you could say things like, hey, 2% change in this is related to a 4% change in that, if the 4 was the B, right? So that's a pretty cool thing about ordinary least squares. The other thing about ordinary least squares is it provides a full fit for the model and a statistical test. So it'll tell you if there's a relationship in the model. That's ANOVA, and it's an omnibus test. Then you can go back into the regression output and look for individual statistically significant relationships. So we get an omnibus test F, and we get a version of a t-test that tells us whether or not each variable is statistically significant or not. And it gives us an R squared, which can be interpreted as a percentage, that tells us how well our model, or all of the variables together, explain the variation in the outcome variable or the dependent variable. So that is pretty cool. Like when we're estimating, I'm working on a paper looking at police education levels. And when you look at all these different things, we can get like 40% of the police education levels, R squared, is related to these 5 factors that we found statistically significant. That's pretty awesome. So it has a lot of explanatory power, and if you have a program like Stata or SPSS or R, we just kind of plug these in there and it spits it out. We don't even have to do the math. What we have to do though is understand what the undergirding of OLS does, what a statistical test does, how to interpret the output, and that's kind of the harder part. Now remember, a multiple regression is a linear prediction, but some things aren't linear. Like a logistic regression allows you to predict like a 0-1. A 0-1 would, like, outcome variable would be like nobody died, somebody died, or somebody survived and somebody died. So we can use like a nominal variable as a dependent variable in logistic regression. Some event happened, it didn't happen. Some condition exists, it doesn't exist. Whereas in a multiple regression, you need an interval or scale. Now, logistic regression operates really similar to ordinary least squares, but it does different things. So if you look over here on the right, a linear regression predicts a straight line, but a logistic regression model predicts whether or not it's 0 or 1. And because of that, you can use a linear regression, but it's going to violate some of those assumptions. So the better way to do it is use logistic regression. Sometimes it's called Logit. It works where the dependent variable is nominal. Okay, so it's just like multiple regression, except it's curvier. There's a variety of ways of estimating this parameter b, but they all have the same functional form. In other words, instead of straight, it's this little curve. And it has really similar output to OLS. Now the way to estimate that, you should look this up in the PowerPoints, is remember how we had y equals mx plus b in the multiple regression. In a logistic regression, since we're not predicting a straight line, the way to get that line to curve is to put 1 over 1 plus e to the, and then you insert that, negative parameter, blah, 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 blah. So in order to try and predict this thing, we have to sort of switch it, and you cannot interpret those the output in the same way that you would a multiple, like an OLS regression output. So what happens in a logistic regression is the stats program estimates the impact of each variable on the outcome, 0 or 1. And what it does is it tries to fit a curve like OLS did. And as it does that, it makes a prediction about whether or not it's a 0 or 1. So based on the independent variable, it tries to figure out if it can predict yes or no for each case, for each of the variables. And then what it does is it puts those into essentially a contingency table. It's a classification table, and it says what we predicted and what we observed. Now, just like a chi-square, we have these observed and expected. The predicted and the observed are the same. And what it's doing is it's measuring the difference. And in logistic regression, instead of an F-test like an ANOVA, you get a simulated chi-square, where the regression is trying to predict whether or not it's a 0 or 1 for each of these variables, for each of the cases. Then it compares what it predicted with what they actually saw. And then you get a chi-square. So instead of an F, when you run a logistic regression, you get a chi-square. So down here at the model, it tells you, the chi-square for the model is 70.74. Sig is 0.000. Sweet. This is awesome. We ran a logistic regression, and we found that there was a statistically significant relationship. Put up a parenthesis. Chi-square equals 70.742, comma, p less than 0.001, which means, and parenthesis. That's how a statistician would write up, we did a logistic regression and we found relationships. Yay! In this one, once again, this is an omnibus test. Is there a relationship anywhere in all of those variables? Yes, that's what the chi-square does. Now we'd go down here, and here's an R-square. Since it's not really an R-square like a correlation or in like in a regression, you have to simulate a chi-square, and we have 3 different ways to do that: Cox-Snell or Nagel-Kirke R-square. You can report either one of those as long as you want. These are a representation of how much variation in the dependent variable can be predicted by the model. Now the model are all these questions. Cool, so what does that look like? Well, question 5A, we look over here in the SIG, is statistically significantly related. So is question 5C. Well, here, so is question Q23, and so is the constant. This one is not related because the SIG is not less than 0.10 or 0.005, or 0.05, I mean. Neither is IC gender or Q15. Now, we'd have to go back into the stats program. The output has gotten a lot better, but essentially, there was a relationship. That's what the chi-square told us. Where was the relationship? Well, here in Q5A and Q5C, Q23, and the constant. Well, what's the direction of the relationship? Well, as Q5A goes up, it's related to what? Well, it's the positive coefficient, so it means more likely to be 1. So as Q5A goes up, we're more likely to have the output of 1 in the dependent variable. This one down here is negative. All of these turn out to be positive influences on that 1. So they have a positive relationship. In other words, it's predicting a 1 instead of a 0. Okay, now what if you just wanted to run ordinary least squares with a dependent variable of 0 or 1? Well, you can do that, and people do that all the time. They call it, anyway, it doesn't really matter. You can do logistic regression, and you can do ordinary least squares. So interestingly, they're really similar. So what I did was I ran the model using logistic regression on the left and ordinary least squares on the right. And these line up where the same question is the same thing over and over and over again. Now, so Q5A is this question, Q5C is this question, gender is this question, current marital status is Q15, Q23 was this one, and Q25 was this one. Totally fine. If you go through, we find that they're statistically significant almost in really, really similar ways. 035, 032, these are the significance. The significance, once again, remember the probability that the null hypothesis is true. You're looking for really small numbers, because if the probability that the null hypothesis is true is very small, it means that the probability that the research hypothesis is very big. And the research hypothesis is that there is a relationship. So the constant is significant over here. The constant is significant over here. Cool. Q5A, Q5C, significant, in the same sort of direction. A lot of people have justified using OLS to use logistic regression because they want to say, well, hey, a 1 unit change in this sort of thing is related to a that unit change in something else. You can do that, but it's not technically correct. And the reason that logistic regression is developed in part is because if you try to estimate a linear relationship with a 0-1 outcome, like a nominal outcome, 0 or 1, you get guaranteed heteroscedasticity. It's a violation of homoscedasticity, because as you're predicting that curve, you're guaranteeing that you're underrepresenting one here and overrepresenting one here, and your errors are not they're not distributed randomly. There's actually a pattern in your error. The other thing about using OLS for logistic regression is that it'll often predict out of range. So at some point, as you're increasing the variables, you're predicting it like, instead of a 0 or 1, you might be predicting like less than 0 or predicting more than 1. And so, we can do it, and people do it, but there's always a better way. And the better way, if you have a 0 or 1 dependent variable, is logistic regression, even when OLS actually works. So stepping back from all of the stats stuff, this is the last of the stats modules. When do I use? What am I supposed to use? How am I supposed to do this? Well, if you're going to compare one sample to a standard, that's a one sample t-test. Grab a sample, see if it meets a standard, one sample t-test. If you're going to compare two groups, you can use t-tests or non-parametric tests. Grab a sample and split them apart. That would be unpaired or an independent samples t-test, because the samples are independent of each other. You can do two groups if that's parametric data. If you're following something over time, that would be a dependent samples or a paired samples t-test, or a paired samples non-parametric test. There are comparable non-parametric tests for all these things. If you have data that are nominal and ordinal, you use chi-square tests and contingency tables. If you have parametrics, you use means, because means are more accurate unless there's outliers. Now, if you're going to test multiple hypotheses at the same time or introduce some additional control measures, both the t-test and the chi-square test and the non-parametric tests are going to be insufficient. So you'll need something with a little bit more power. ANOVA is one of those tests that's used very routinely in trying to see if there's a relationship somewhere in the data. Comparisons of means and variations. For my discipline, ANOVA would never be sufficient, but for psychology, it's more than sufficient. So what we do in my discipline is use regression, ordinary least squares regression, or logistic regression, ordinal logistic regression, multinomial logistic regression. There's all sorts of these things. But what they do is the dependent variable, the outcome variable, determines what kind of regression you're going to end up doing. For interval ratio, ordinary least squares works. For logistic regression, it has to be nominal data. For ordinal logistic regression, you're looking at ordinal level data. For multinomial logistic regression, it's where you have multiple nominal variables. So there's always something that you can do. If you want a really good book, there's a book called There's a Stat for That. It's by Bruce Fry. It tells you why you use certain estimating techniques and why you use certain kinds of formulas versus others. Most of all, if you can Google it, you'll figure it out. If you understand the basic principles about what we're trying to do, like testing multiple hypotheses, what kind of dependent variable do you have, what are some of the strengths of one of these things, you'll be more than adequately ready to start statistical testing using a statistical software program. Look for the things that you know. Look for some omnibus test like ANOVA or an omnibus chi-square test. Look for T's, look for F's and chi-squares. Look for the things that you think are the measures of difference between what we observe and what we expect, or the measures of difference between two samples. Look for the sig or the p-value. The sig is the same as the p-value. That's the probability of no relationship. Probability of null hypothesis is true. Look for the parameter estimates, the B. What is the strength of that relationship? Is it big? Is it small? Look for the sign. Almost always, a positive B means that there's a positive relationship, and a negative B means there's a negative relationship. So as one goes up, one goes down, or they both go up. Look for these things as keys, and if you don't know about what they all mean, go ahead and Google it. That's a pretty good start.